Okay, we're back, and I'm going to spend the next videos just going through examples of problems with different unknowns. This video I'm going to talk about unknown surface concentration. We talked last time about unknown concentration at depth x. So my example, I've got the steel is 1020. That tells us our concentration of the overall steel. Temperature is 1100 C. The carbon concentration at a depth is 0.4 weight percent carbon. The depth is 1.5 millimeters. We get a duration of 12 hours, and we're asked to find C sub s. So the first step is to calculate diffusivity D. The constants are 2.3 times 10 to negative 5, that's D0, and Q is 148,000 joules per mole. So D at, let's see, we have 1100, so we've got 1373 K. D would be equal to this D0 value of 2.3 times 10 to the negative 5 meters squared per second. E to the minus Q is 148,000 divided by 8.31 times 1373. So the power that E is taken to 148,000 divided by 8.31 divided by 1373, and the negative of that. So I get negative 12.97 for that power. Take e to that value, and I get 2.33 times 10 to the negative 6. And I just want to check that, make sure I got that right. Yep, that's correct. So multiply that by 2.3 times 10 to the negative 5. And we get that D is equal to 5.35 times 10 to the negative 11. Okay, I apologize for that break. Um, so we've got this is equal to 0.486. So 0.486 is equal to c sub x 0. Sorry, 0.4 c sub x is 0.4 minus c0, 0.2 divided by my unknown cs minus 0.2. So c sub s is equal to 0.4 minus 0.2 divided by 0.486 plus 0.2. So my C0 is 0.6, or sorry, my C sub S. Surface concentration has to be at least 0.6 if I want to be able to get those results at the depth given, 0.0015. All right, so we had values. We had C0 of 0.2. We had Cx of 0.4. We had Cs of 0.6. We had D of 5.35 times 10 to the negative 11. We had X of 0.0015. We had T of 43,200 seconds. So going to keep all those things in mind because now we're going to talk about potential follow-up questions. So there's two different kinds of follow-up questions. One of the kinds of follow-up questions, the first one I'm going to show you here, can be really simple if you know the shortcut. So that would be, hey, what would C sub x be if C sub s was something different? So again, remember that our equation on the one side of the equation we have Cx, Cs, and C0. The other side of the equation we have x and time and d. So in this case, we're changing one of the variables on the left side of the equation, and we're asked for another variable on the left side of the equation, which means that everything on the left together is the same. So let's look at that as an example. Here's my original problem down here at the bottom. And in the follow-up, we're asked to change C sub x if C sub s is 2.2. What would C sub x be? And everything on the right side of the equation is remaining constant. All of this is the same. So whatever we had for Cs minus C0 or for Cs minus C0 before, we should have now. So 0.4 minus 0.2 divided by 0.6 minus 0.2 should be the same as what our current conditions are. We're not changing C0 or Cx. We're actually trying to find Cx. But we're changing C sub s to 2.2. So So I don't have to use the error function table. I don't have to start from the beginning. My left side of the equation here is 0.2 over 0.4, so this is about 0.5. I think we had a 0.848 or something. And I can just figure out c sub x by taking 0.5, multiplying it by 2.2 minus 0.2, or 2. So that gives me 1. And that's equal to c sub x minus 0.2. So I have that 1 is equal to c sub x minus 0.2. So my c sub x value under these circumstances will be 1.2. So there's a possible follow-up question where you're changing something on either the left or the right, and you're asking for something on the left or the right, the same side. Then you can just jump to a quick assumption that the total of what's on the other side of the equation is constant. The other kind of follow-up question is where I'm changing time, which is on the right side of the equation, and I'm asking for the effect on c sub x. So in this case, I do have to basically start from the beginning. C sub x is it's my new unknown. So I've got c sub x minus 0.2. And we're going to go back to the c sub s we had before, which was 0.6 minus 0.2. All of that is equal to 1 minus the error function of x is the same, 0.0015. 2 square root, not changing temperature, so d is the same, 5.35 times 10 to the negative 11, but we are changing time. It's 8 hours instead of 12. So 8 hours is going to be the equivalent of 28,800 seconds. So this whole quantity would be z in the error function table. So let's see, what do we get for that? So I have that the sum of all of this, or the product of all of this, is 0.604. And you should always try to run it through twice just to make sure that you did that calculation correctly. Yep, I got the same value. So now I can use my error function table, putting z at 0.604 to find out the value of the error function of z. So I'm going to skip to this page so I can see my table. And I have z of 0.604. And I'm trying to find the error function of that value. So I look in the z column, awfully close to 0.60. And I would say if you're rounding off and you get to 0.60, you could just use the table directly. You don't need to interpolate. So I'm going to say that's approximately the same as 0.60. And if that's true, then error function Z is 0.6039. Which is right there. So 1 minus that is going to be equal to 0.396. And that's equal to C sub x is my new unknown, minus 0.2 over 0.6 minus 0.2. So I take 0.396, multiply it by 0.4, and then I add 0.2, and my new C sub x is 0.36. So when you get a follow-up, you could just plug and chug, do it the way that you always have, or you could take a good look at the follow-up and see if you can shorten your solution by noting that all of the unknowns have stayed on the same side of the equation. All right, so that does it for video 3.